Welcome to our comprehensive guide on electric vehicle technology. I'm Yogacharya Basu, and I'm so excited you're here. Today, we're going to break down some essential EV concepts, making them easier to understand and remember. Think of it like this. EVs are like the coolest science experiments on wheels. We're talking about batteries, motors, circuits. Oh my, by the end of this video, you'll be able to impress your friends with your EV knowledge. Get ready to charge up your brains with some electrifying information. Hey everyone, it's great to be here with you today. I'm Yogacharya Basu, and I'm thrilled to guide you into the world of EVs. My background in electrical engineering sparked my interest. I pursued a master's in yogic sciences. For 7 years, I've been a field support engineer at Indus Towers. My goal? To build affordable EV infrastructure in rural India. So why did I choose to embark on this EV program? It all boils down to my vision, a world powered by sustainable energy. This program is like the perfect electric engine to propel me toward that goal. It provides the technical knowledge and industry experience I need to turn my dreams into reality. It's not just about understanding the technology, it's about using it to make a real positive impact on our planet. Let's talk about why EVs are creating such a buzz. One word: emissions. Traditional vehicles are major CO2 contributors harming our planet. EVs can reduce emissions, especially with renewable energy. Take Norway, for example. They use 98% renewable electricity for EVs, but we need a holistic approach for sustainable EV ecosystem. Now let's talk about e-waste. Just like any electronic device, EVs generate e-waste, particularly from their batteries. But fear not, my friends, because solutions are out there. Think of it like this. Just as we recycle paper and plastic, we can recycle EV batteries to recover valuable materials. Companies like Tesla are leading the charge with closed-loop recycling programs. We can also reuse rare earth metals found in these batteries, reducing the need to mine for new resources. Ready to peek inside an EV? It's simpler than you think. The electric motor, controller, and battery work together. The motor converts electrical energy into mechanical energy. The controller regulates electricity flow for a smooth ride. All systems aim to get you from point A to point B using electricity. All right, let's dive deeper into the fascinating world of motors. These incredible devices are the workhorses of our electrified future, converting electrical energy into mechanical energy through the magic of electromagnetic induction. Imagine a wire carrying an electric current. Now place that wire within a magnetic field and watch as a force acts on the wire, causing it to move. That, my friends, is the fundamental principle behind how motors work. Let's zoom in on the electronic components that make electric vehicles tick. These components control electricity flow, ensuring optimal performance. The inverter translates battery direct current to motor alternating current. Converters adjust voltage, ensuring each component gets the right amount. The controller orchestrates the motor for a smooth ride. Let's get back to basics and explore the world of direct current motors. These motors are all about direct current, using it to produce torque, that twisting force that gets things moving. You can picture a direct current motor as having a few key parts: the stator, the rotor, the commutator, and the brushes. Direct current motors are like the reliable workhorses of the motor world, found in a wide range of applications, from conveyor belts to electric scooters. Now, let's talk about alternating current motors. These motors operate on alternating current, which, as its name suggests, constantly changes direction. Inside an alternating current motor, we have a stator, which creates a rotating magnetic field. This field interacts with the rotor, causing it to spin. Tesla's high-performance Model S uses alternating current induction motors to achieve those impressive speeds and acceleration. Now it's time to put on our thinking caps and explore some electrical circuit principles. First up, we have Kirchhoff's voltage law, or KVL for short. This law states that the sum of all voltage drops in a closed loop must equal the supply voltage. Imagine a series circuit with a 12-volt battery connected to a 4-ohm resistor and a 2-ohm resistor. According to KVL, the voltage drops across the resistors must add up to the battery voltage. Next up, we have Kirchhoff's current law, also known as KCL. This law is all about the flow of charge, stating that the total current entering a node, a junction in a circuit, must equal the total current leaving that node. It's like a traffic intersection for electrons. Let's put KVL into practice and design a simple circuit. We'll start with a 10-volt source and connect a 2-ohm resistor and a 3-ohm resistor in series. Remember, in a series circuit, the components are connected in a single path, like links in a chain. Using Ohm's law, voltage equals current times resistance, we can find the current flowing through the circuit. 10 volts divided by 5 ohms equals 2 amps. Now we can calculate the voltage drop across each resistor. 4 volts across the 2-ohm resistor and 6 volts across the 3-ohm resistor. Now let's see KCL in action with a parallel circuit. In a parallel circuit, the components are connected on separate branches, providing alternative paths for the current to flow. Imagine a 12-volt battery connected to 2 parallel branches. The first branch has a current of 4 amps, and the second branch has a current of 2 amps. According to KCL, the total current flowing from the battery should be the sum of the currents in each branch. Let's talk about the unsung hero of the EV world, the Battery Management System, or BMS for short. This sophisticated system is like the guardian angel of your EV's battery, ensuring its safety, performance, and longevity. Think of the BMS as the brain behind the battery, constantly monitoring its vital signs, including voltage, current, temperature, and state of charge, SSOC. The BMS ensures that the battery operates within safe limits, preventing overcharging, over-discharging, and overheating. It also balances the cells within the battery pack, ensuring that they all charge and discharge evenly. Imagine this. You're on a road trip in your EV, and you need to know how much charge you have left. That's where estimating the battery's state of charge, SOC, comes in. Think of SOC as the fuel gauge for your EV battery, telling you how much juice you have left in the tank. One common method is Coulomb counting, which keeps track of the amount of charge entering and leaving the battery. Another method is open circuit voltage, which measures the battery's voltage when it's not being used. Let's unravel the mysteries of the lithium-ion battery, the heart that powers most EVs today. These batteries are like energy storage superheroes, packing a lot of power into a compact package. Picture a lithium-ion battery as having 2 electrodes, an anode and a cathode. During discharge, lithium ions flow from the anode to the cathode, releasing energy that powers your EV. Now let's explore the different types of batteries used in EVs. While lithium-ion batteries currently dominate the market, other contenders are vying for the top spot. Lead-acid batteries, the veterans of the battery world, are still used in some EVs, particularly in hybrid vehicles. They're inexpensive and reliable, but bulky and heavy. And then we have solid-state batteries, the new kids on the block. These batteries use solid electrolytes instead of liquid ones, potentially offering even higher energy density and improved safety. Let's compare 2 popular motor technologies used in EVs, permanent magnet synchronous motors, PMSMs, and brushless DC motors, BLDCs. Think of them as 2 different dance partners, each with its own unique moves. PMSMs are known for their smooth, sinusoidal back EMF, which means the voltage generated in the motor windings follows a smooth, wave-like pattern. BLDCs, on the other hand, have a trapezoidal back EMF, which means the voltage has a more abrupt, stair-step-like pattern. Get ready for a cool EV feature, regenerative braking. This innovative technology turns your EV into a mini power plant, recovering energy that would otherwise be lost during braking. Imagine driving your EV and approaching a red light. As you step on the brake pedal, the electric motor switches roles, turning into a generator. This captured energy is then fed back into the battery, replenishing its charge. Let's revisit PMSMs and BLDCs, this time focusing on their structural differences. PMSMs have a continuous winding on their stator, creating a smooth sinusoidal magnetic field. This smooth field is what gives them their smooth back EMF and high efficiency. BLDCs, on the other hand, use segmented windings on their stator, creating a more stepped trapezoidal magnetic field. Fasten your seatbelts because we're about to explore the superposition theorem, a powerful tool for analyzing circuits with multiple sources. This theorem allows us to break down complex circuits into simpler ones, making them easier to analyze. Imagine a circuit with 2 voltage sources, a 10-volt source and a 5-volt source, along with some resistors. The superposition theorem tells us that we can analyze the circuit's behavior by considering the effect of each source independently. Thank you for watching. We hope this guide has made EV technology concepts clearer and more memorable. Remember, the world of EVs is constantly evolving, with new innovations emerging all the time. So stay curious, keep learning, and embrace the exciting future of electric mobility.